Hello everyone. The question of the day is, what is the Apache Hadoop ecosystem? My name's Brian Kafferkey, and if you're like me, you've probably been mystified by all the different terms and names and everything. And honestly, a lot of the names in the Hadoop ecosystem don't even really have the same classification type. Like Kafka is a major philosopher and wrote some very good books. But what does that have to do with a cute little elephant? I don't know. And then you've got things like Zookeeper. So it's kind of a weird thing. And my goal here today is to help you demystify this. And actually, preparing for this helped me demystify it for myself. There's a lot of different pieces, a lot of different tools, but we will make this clear before we're done. At least that's the goal. So I want to start with golf clubs. And the reason is because I think golf clubs is a good analogy I can use here. I'm not a good golfer, but if I were a good golfer, I know how to use all these different clubs because each club has a different purpose. For instance, the drivers, those are the ones with the big golf club head. Those are meant to hit long distances, right? And the lower the number, I think it is, the further the distance. And then you get to the irons, which are more intermediate distance. And then if you get close, which I usually take forever to do, but if you ever get close, then you can use the putter to get in the hole. And then I'm pretty good with the pitching wedge because I end up at the sand traps. So you can use the pitching wedge to get out of sand traps. And so that's kind of his whole thing. And my favorite club is the 5 iron roughly because I can hit that fairly well. It's short. It's one of the easier ones to control. The point of this is each golf club has a different purpose. And so I want you to keep that in mind in the same way in Hadoop, in this ecosystem, each tool, regardless of its cute name, has a different purpose. And so it's like pulling out the tool that you need at a given point in time and say, okay, there's this tool and there's this tool. There's HBase and there's Kafka and there's Hadoop. What tool fits the situation? And this is true really in any kind of IT solutions, any kind of programming solutions. Different tools fit different purposes. They have their strengths and weaknesses. I've yet to see the perfect tool. That's the one I keep looking for, that silver bullet that everyone always talks about. Have not found it yet. But we'll see. Now, before I get into the Hadoop ecosystem, I do want to talk about a concept which is really critical to any sort of talk about big data, which is scale up versus scale out. So when people talk about scale up, what they really mean is this is the old way of doing things, back in the mainframe days even. The idea is you just add more RAM, add more hardware, etc. to do more work. So imagine, you go from saying having to lift 100 pounds, we'll call that the workload, and you say, okay, now it's 200 pounds. So you send Barry here, the guy in the left, go to lift more weights, beef up, come back, now he can handle 200 pounds. But let's face it, at some point, one person can only do so much. And the same is true of a computer. The speed of CPUs has actually kind of plateaued at this point. There's only so much memory we can put on things, and the amount of data that we need to process has just greatly exceeded the ability of one machine to handle it. And so the big internet companies hit this problem first. Your social media sites sort of finally realize, like, we just can't do this with our typical scale-up solutions. And that's where scale-out comes in. All right. So the idea behind scale-out is one person may not be able to do it, but maybe 2, 5, 10, 20. If we split up the work, more people involved, we can get more done. So let me use an analogy. Suppose we have a phone book. And what our goal is, we want to find all the people in the phone book who live on a street named Main Street. That's all we want to do. Well, one person trying to go through the entire phone book and scanning, trying to find all the people on a main street, regardless of the city, could take a long time. So let's say we split up the phone book and we give, by the letter of their last name, we give it to each person. So we split it up, everybody gets a last name of the alphabet type thing, and they search for that. Well, it seems pretty common sense that it's going to go a lot faster that way, right? And then one person at the end, this whole group of people are nodes. Each person is a node. We'll call them that. And the whole group of people is called a cluster. And you'll have like a cluster manager, a coordinator, who can collect all that stuff at the end. So each person gives them a little slip of paper and says, this is the names I found. Great. So that's kind of the idea of scale out. We can get it done faster by employing more computers, or in this case people, but just swap out now computers, and we got the idea. Nodes, computers, we're good to go. All right, so let's take a look at this very busy, I admit, slide to kind of demystify it and break it down so we can sort of understand what is the Hadoop ecosystem. First of all, the Apache project itself is really a collection of things, so lots of things go in. And a lot of times when people, company or something, develop something, decide they want to go open source with it, just make it free and give you the source code and everything, it gets thrown into the Apache project, and specifically here the Apache Hadoop Ecosystem project. And I think of this a little bit like, my house, we have a kitchen drawer, and people just, kind of just throw different things in there. It's kind of like where you don't know where to put something, it goes in the kitchen drawer. So, you got flashlights, you got batteries, you got lighters, whatever in there. And you kind of comes a little confusing why it doesn't seem to be organized. It's not quite that bad, but I think a little bit sometimes the Hadoop ecosystem seems like that to me as well. All right, so let's take a look at I'm going to start with the sort of beginning of all this, which is Hadoop. And if we look at the sort of 3 stacked tiers there, MapReduce Hadoop, so Hadoop MapReduce, Hadoop Yarn, and the Hadoop HDFS, that's kind of where it all began. So let's talk about that a little bit. So the idea was, again, we want to scale out. We want to be able to employ a lot of computers, and the idea also is cheap computers. So we don't need heavy-duty machines. These could be machines we're going to throw out. These could be junk machines. So there's a lot of resiliency built into Hadoop because we expect that 20-year-old machine that can't really do much. It may fail, so we got to allow for that. And Hadoop has all kinds of stuff built in to do that. So we start with the idea of our card searching or a phone book search, and that's our request. And we format that a specific way, which is called MapReduce. So we have to really format this request. It's not SQL. It's not something very intuitive. It follows a model called MapReduce, and originally that had to be written in Java. So we write our MapReduce request, and then we submit it into the system. And the system that gets it underneath is called Yarn, Yet Another Resource Negotiator, is apparently what that stands for. I know, right? Great name. A lot of times in IT you see now yet another something, which is what the YAR stands for. But anyway, so we've got the resource manager, which is going to take what you asked for and split it up into multiple requests. It's going to make sure that that set of instructions gets to the person or the node that needs it so they can process it, and then find out who's at Main Street and then send it back. So that resource negotiator there is actually handling the request itself and getting the work done. Underneath that is the Hadoop file system. It's called HDFS. And HDFS is really interesting because we've all used file systems, right? You copy a file onto your drive, etc. You can go look at it, you can move it around. HDFS acts like a file system like that, but in actuality, when you copy a file to it, it actually replicates the file. It copies it across the nodes, like when we talked about giving the phone book out to different people. It also creates extra copies of each copy. So it splits up the data and copies it across the nodes, as we mentioned, but it also creates extra copies of those segments of data so that if anything happens, one of those machines fails, it can still recover and keep moving, and you don't lose your data and you don't lose your process. So that's kind of the overall idea of the Hadoop MapReduce setup. Again, you send your request through MapReduce, it goes through Yarn, Yarn coordinates the work. HDFS is actually copied out those copies that we talked about by last name or whatever, so it's all partitioned out. And then the request can happen, and each job will search for, each node will search for the what you asked for, which is the Main Street people living at Main Street. And then it goes back up, and the cluster manager essentially collects the results and gives it back to your original request and says, here's your results. Great. A couple of things to point out about how that's working. One, underneath the covers, there's massive amounts of jobs being submitted. It's really a batch queuing system that's dynamically creating and sending off batch jobs. And it has to manage that and coordinate that with other demands on the system. So there are other things potentially going in there. And so it is a batch-orientated system. It is not designed to be something where you immediately submit a request and expect it to come back right then and there. This is a sort of gonna go for coffee, maybe go for lunch, maybe come back tomorrow kind of scenario. So it's that whole batch orientation. And I think it's important to bear in mind that Hadoop is really the first major big data, open source, popular solution that came out. So in fairness to it, it was designed like, wow, this is able to handle a petabyte of data. That was massive and impressive at the time. Since Hadoop came out, there have been a lot of new takes on it and different ways to approach things, and that's partly what's going on in the rest of the Hadoop ecosystem. Okay, so I think I've covered Hadoop, at least I hope I have. questions can certainly go in the comment area, and I'll try to answer those. And by the way, you can look me up on LinkedIn if anyone wants to connect. I should have mentioned that. But let me continue. So let's kind of work our way out. There's a thing called HBase and Cassandra. Now these are very closely related, and I've been doing research trying to figure out when you use which and where, but let me just talk about a few differentiators between them. So HBase, if you look at Hadoop, it's sort of a distributed file system and designed to query, but it's not designed like a database. So if you want it to be able to sort of persist the data and have it kind of simulate like a table so that you could query and do things with it, HBase is kind of designed to do that, but it's designed to do it in a big data way. So if you imagine you're somebody like Facebook and you want to be able to store a massive amount of data very quickly, then you could use something like HBase or Cassandra to do that. So it's using that big data distributed. HBase is coupled with HDFS. So it does work on the Hadoop file system, and it does use that whole MapReduce approach. So it's massive scaling, and it's doing things under the covers. But it can scale really well. But it's essentially sort of conceptually, it's like one sort of massive data store on these clusters. One differentiator, now built in, HBase also does not have any kind of easy to use abstractions. So by itself, HBase does not, for instance, support SQL. Now there was a project, and there is a project in Apache, which I don't show here, called Phoenix. And Phoenix is kind of like adds a SQL layer over HBase. All right, Cassandra, which actually has built in something called CQL, Cassandra's QL, which is a SQL-like language. So that's one differentiator. But a really interesting differentiator with Cassandra versus HBase is it has a multi-copy distribution. In other words, it will actually have a full copy of the data in multiple places, which is ideally suited for geo-replication. And the idea of geo-replication, if you think of data centers, and it's very big in the cloud now, is I may have a data center in Asia, I have another one in Europe, and another one in the United States, and I can service requests whichever's closest to the requester. So it lets it create lower latency and faster response to whoever's working with it, but then what it will do is replicate that change to the other nodes, the other copies. Okay, so it's going to be able to replicate that. So it's similar to what databases have done for years, where they kind of use log shipping or something, where they're syncing up data, but it's pretty fast, and the idea is that we have multiple copies, and we're able to work with it very performantly. And so that's kind of the two things here. So I invite you to go look at Cassandra and HBase and kind of query which one, if you want to use one of those, makes sense. Neither one is designed to really fully support what a relational database with. For instance, they don't support joins. They do both, depending on how you set it up. For instance, with Phoenix, you can do some sort of SQL type stuff, but there's some limitations to that. So the key with either one of them is, high throughput, not necessarily functionality in terms of that type of thing. So that's HBase and Cassandra. I do want to back up and go back to Hadoop, because I meant to talk about a few other things here. So there are three little pillars little boxes over the Hadoop MapReduce. And the first one I'm going to go is in the middle, because I think it's the most useful to me, which is called Hive. So MapReduce is not easy to write. I remember when Hadoop first came out, and I got the book on MapReduce and looked at Java and looked at all the stuff, and I'm like, wow, it's a lot of work just to, granted it scales, but it's a lot of work to just say who lives at Main Street. Not as easy as saying SQL. Well, Hive is the answer to that. Hive is a abstraction layer over Hadoop that lets a person write SQL, and then it submits into the system and generates a MapReduce job for you, and then goes off and satisfies the request and comes back. Great idea. Hive, to me, without Hive, I don't think I could use Hadoop at all. So good job to have Hive. But sometimes you need to do ETL kind of work. You need to extract, transform, load data, move things around, and that's where Pig comes in. So Pig has its own sort of language. It's designed to do ETL work, not as user-friendly as SQL, but it can do things for you kind of for that ETL type of purpose. And finally, on the leftmost of those three boxes is Mahout. And what Mahout is designed to do is support machine learning. So it's a machine learning library that allows you to use MapReduce and the whole Hadoop system to scale up or scale out. That's an important thing to realize. When you do machine learning, use certain libraries, whether it's classification models or deep learning or whatever it is. And what a lot of people sort of new to machine learning may not realize is that the open source functions used to do this, the packages or modules used to do these these models, are not designed to scale out or even up in some cases. So what I mean by that is you use typical R, say a classification model, will only use a single CPU. It won't see that there's 10 CPUs or something it could be using and then map out and use all of that, or use all of the resources of the machine. So it's very linear. It's kind of designed, the open source Python and R by default, the libraries are designed to really be client based, like Excel or something. And so it's not really great for performance and scale. So to get around that, if you want to scale out to Hadoop level, petabytes, you can use the Mahout library. But it does mean you have to sort of rewrite and retrain your algorithms by that library. Okay, and that's a common pattern, by the way. You'll see even with SQL servers, machine learning server built in, there's that rewrite, and they have certain functions for that. Okay, so now we've talked about Mahout, Hive, and Pig. I think we've covered the Hadoop system. We've looked at HBase. We've looked at Cassandra. Let's kind of step aside and look at Zookeeper. Not a lot to say about Zookeeper other than we don't need to think much about Zookeeper. It's just one of those words that keeps popping up when you talk about Hadoop and can be confusing. Zookeeper is used by HBase and I believe by some other things under the Hadoop file system, the Hadoop ecosystem. And what it does is it's a distributed system coordinator. So it provides services to HBase for one thing. And I think it's also used in some other places, but the idea is it's really not something you would employ directly. It can be employed by the other tools within Hadoop. Okay. So we'll look now at Storm. When I think of Storm, I think basically the idea of Storm is it's meant to support streaming analytics. So heavy duty streaming, unbounded, that kind of thing. Good example might be Internet of Things. You've got IoT applications, massive amounts of data. You could go through Storm and it could support that sort of streaming. So that's the idea of Storm. Might want to use that if you're doing those types of applications. This thing called Solar or Lucerne Solar is another thing that's not for streaming. That's actually for sort of, if you think about really like Google search or Bing search, you're typing things and you're searching and it's able to massively go out and it's indexed all this data, and as you type it's giving you like IntelliSense. It's really quick and responsive. That's the idea of Solar. It's meant to give you in your applications you can apply this and get massive scalability for searching. So it's a great thing. You could be like, if you think of some major internet company, it's got a lot of products. Can't think of any, right? But you get a company that's got a lot of products like Amazon or something, and they have to they want to be able to support fast searching. This would be an example of where they could use something like that. So that's kind of the idea there. All right, let me go now to the tier at the bottom here, and I am ignoring Spark for the moment because I want to kind of handle that as a special case almost, because it's just a very interesting area. All right, so at the bottom here, we've talked about streaming with Storm, but what about streaming with Flume? Flume is really, I guess the first use case they talk about when you look at Flume is something like web logs. So you've got massive amounts of data coming in. If you ever look at logs, it's like every click you click on in the internet is stored, goes to a log, and that's what Flume is designed to be able to handle that volume. But it's also got sort of an aggregation feature support, and it kind of almost ETL-ish in nature. It can channel what you're doing, do some aggregation, and then write it somewhere. And generally the idea with Flume is to kind of redirect and write that data performantly somewhere. Use a store. So the idea is something like weblogs, a little different than Storm, really kind of different use purpose. It's a little more specialized. All right. Kafka. When I think of Kafka, think of things like message queuing or queuing in general. It's a queue. And the idea is, and usually what Kafka is used for is if you're doing something like IoT or something and you're streaming a lot of data in, it could be coming really fast. If you can imagine some, massive amount, imagine, Bing traffic, we'll say, or Google traffic, a lot of stuff coming in, and you got to be able to handle it. If you don't want to drop anything, a good way to handle that is to sort of buffer it, right? You want to get in the requests and then be able to handle it a little bit more, under more control. You don't have to just have this massive file streaming in your face and you're going to drop something, right? So think of it like a funnel, but think of it like a big container, like a pool, collecting all the water from maybe multiple fire hoses, and it's not overflowing, so that's great. At the bottom maybe you have a hole, And so like a funnel, it's just like letting some of it sift through at a time. And that's kind of the idea behind Kafka. Kafka's sort of where you channel it in, and then it can sort of buffer it up and then let it flow out as it under a more controlled manner so that you don't lose anything. Okay, finally Scoop. Scoop is actually a very specialized type of tool, but important nonetheless. What it's really designed to do is support input and output from Hadoop's ecosystem to relational data stores. So your SQL Server, MySQL, Postgres, etc. That's the idea of Scoop. All right, so we've talked about a lot of tools, and now we're going to talk about the thing I really want to talk about here, among other things. I like all of it, but I really wanted to talk a little bit about Spark, because Spark has actually become by far the most hottest, most popular area of the Hadoop ecosystem. And it isn't really something that was part of Hadoop. It's something that was designed by somebody as a project in college, basically. And the idea was to provide big data support, a tool that would do this really well. I do think that Spark seems to have learned from Hadoop in some ways. I've never heard anyone say whether that was trying to replace Hadoop or whatever, but it certainly seems that it took things that Hadoop did well and it copied them, and it took things that were limitations, I think, to Hadoop and improved upon it. And I'll explain that as we go. But the first thing that Spark does is it's not batch orientated, which is great, because personally I don't like to wait for everything in a batch. I like to say, give me the answer now. Sometimes you're going to wait, and Spark can do that. It can sort of push things off and do it more like that, but it can support real-time analytics, real-time queries. How does it do that, though? Well, one of the things that's really interesting about Spark is a new thing that's kind of come along the last few years is doing things in memory. Writing to disk is very time intensive. It's I/O bound, and Hadoop does that. HDFS is always reading and writing against physical storage. So one of the things that Spark does is says, here's an idea. Why don't we just bring everything into memory and we'll do everything in RAM? Granted, you got to have a lot of RAM to do that, but hey, we're distributing similar to Hadoop. We'll distribute it the same way, cluster, nodes. We have 1,000 machines. We'll just give a chunk to each machine, and it just has to hold on to what it needs in memory, and then we'll do that searching. So by doing that, it can achieve speeds up to 100 times faster than traditional Hadoop. So that's a huge improvement. But there's some other things too that's really interesting with Spark. For one thing, built into Spark out of the box is support for SQL. So if you're a data person, interesting about NoSQL, NoSQL started out meaning not supporting SQL, NoSQL. Then it turned into not only SQL, because what's happened is SQL's making a big comeback. Relational databases, maybe not expanding as much, but the SQL language is actually regaining ground because it's a very good way to be able to access, query, etc. data. It works, and that's what it was about. As a result, Spark supports SQL out of the box, which I think is awesome because I like SQL. Okay, another thing, Spark has support for highly scalable machine learning, and it uses a library similar to Mahout. It uses something called MLlib, or MLlib. It's a machine learning library. Very intuitive. Actually, I like the naming here too, because it may not be a cute name, but it is something I understand. So you get machine learning library. Again, you have to take your open source functions that create your models and migrate them into the MLlib, but you can do that. And these things in both Mahout and MLlib, as I mentioned, it may not support all of the things that the open source version supports. So you have to kind of lagging a little bit behind, but there's a lot of good support there. You also have something called the GraphX support, again, built in. If you've heard of graph models and things, the idea is kind of like they have these ideas of sort of nodes and edges. But the idea is you're going from point to point and you're navigating. So I think one of the early use cases for this would be social networks. You know, I'm connected to Mary, and Mary's connected to John, and John's connected to, 3 other people, and you can picture this navigation. So if I wanted to know, how do I get from Brian to Harry over here, you might have to go through all these different connections. So that's one example of a graph type thing. Graph databases kind of support that type of idea. The other thing that you can get with graph would be something physical, like a geospace kind of thing, or GIS type stuff. So you picture your mapping. I want to know how to get from Boston to LA. Well, I can go to this city, to this city, to this city, to this city. Or maybe I want to use air flights. Well, then I can really picture what airport. So airport to an airport to an airport. and I could find different ways to navigate. And then one of the things I could do is try to use that as a way to find the most efficient way to navigate. So there's a lot of good use cases for graph databases, graph interfaces, and GraphX is sort of built-in support in Spark to enable that kind of conceptualization and work within Spark. And finally, Spark streaming. So Spark, again, is like Hadoop. It can support massive amounts of data, and so it has streaming support built into it. So you might go through Kafka to sort of, like I said, buffer it up and then spin it right into Spark streaming, and then you could do like analytics and things like that with it. So that's one thing that's really great with Spark. And as I mentioned, it's definitely the hottest area. By far, the most work going on now in big data is in Spark, because there's so much cool stuff you can do. And one of the things I also really like about it is that it supports other languages, which is not true with Hadoop, built in at least. It supports Scala, which is really sort of the Spark language, which is a little bit like Java. Then it also supports Java, and it supports Python and R. Now Python and R is supported through R is supported through a package, Spark R, and Python is supported through a module, which is PySpark. But with those, you can actually manipulate and do everything in data frames. Spark 2.0 has really moved away from what they used to call the resilient distributed data set to just data frame support. Data frames are essentially in-memory tables, and so you can just think in terms of like regular table ideas, filtering, searching, etc. And he mentioned SQL support, so you can really abstract and think more intuitively about the data and how you're using it, and not have to get into sort of the implementation of how it's doing it under the covers. And if I had to be a little bit critical, I mean, it's amazing that Hadoop, what it does, but the thing about MapReduce that to me was a problem is it didn't abstract enough away from the implementation, and that's why Hive and things eventually came out. But I think that Spark out of the box realized they had to abstract more away from it so that you could work more on the business problem and not on how it's implemented under the covers. All right, so that's my feedback. I hope you like this, and I'm going to wrap up in 1 second. I just want to look at that. So coming back to this, again, when you look at this ecosystem, the idea really behind the whole ecosystem is each product, each thing has a different purpose. There's a little bit of overlap between some of them. I think Spark sort of stands on its own, almost as its own miniature ecosystem. And really, Spark, ultimately, because it is in memory, does leverage other things. So you might have a lot of data stored in Hadoop and HDFS, and you just want to suck it into Spark and use it for certain things. And you can certainly do that. In Microsoft now they have Azure Databricks, which is a big thing I'm really excited about. And a new thing that they're pushing, relatively new, it's new to Azure certainly, is something, I don't think it's officially in GA yet, so I want to be careful to say that, but by the time you watch this video it may be, which is called Azure Databricks Delta. And so what Delta is going to allow you to do is something more consistent with sort of data warehousing and all kinds of cool stuff within Spark. So that's exciting, and that's going to allow probably a lot of what you saw in the ecosystem now. You can do almost everything right within Spark with Databricks and all that good stuff. So wrapping up, please subscribe, please share with your friends and all that good stuff. I hope you like this. Put comments in, and I'll get to those and answer those questions. Reach out on LinkedIn and connect. Let me know you're watching this stuff, and have a good day. Thank you.